Hi, my name is Manik Singhal,
And I'm Sid Parida.
and for our 595 final project, we studied catastrophic forgetting in artificial neural networks and implemented a couple of algorithms to overcome it for two simple network architectures.
In this presentation, we'll first talk about what catastrophic forgetting is, and then talk about how we implemented a solution proposed by Google DeepMind to overcome catastrophic forgetting. Then Manik will talk about the experimental setup we used to test our algorithm, and then finally present some of the results that we obtained. And we'll end the presentation by talking about certain modifications that can be done to this algorithm to improve the results. The goal of neural network research in recent years has been to mimic and try to even surpass general artificial intelligence systems. In order to do that, these systems have to be capable of learning and executing multiple different tasks. And these tasks don't necessarily need to be learned at the same time. Now, to do this, continual learning is very important. But what is continual learning? Continual learning is the idea that an artificially intelligent system should be able to learn multiple tasks. However, both of the tasks or all the different tasks being considered need not be learned at the same time. For example, the system should be capable of learning one task and then subsequently learning another without sacrificing performance in the first task. Within continual learning, we can consider two scenarios. The first, in which every task has the same output space, and the second, in which the tasks are complementary and the output space changes. Now, to draw an analogy with human behavior, example of the first task would be language interpretation. For example, a human can learn how to say understand French and then subsequently learn how to understand Spanish without forgetting how to understand French. Now, in the second scenario, a common example of human behavior would be, say, when a human learns how to ride a bicycle and then learn how to swim without forgetting how to ride a bicycle. Now, in modern neural network algorithms, continual learning suffers from a problem called catastrophic forgetting.
So, what is catastrophic forgetting? Catastrophic forgetting is essentially the phenomenon where you forget important parameters from a previously learned task while learning on the new task. So, how do we combat catastrophic forgetting? An intuitive solution would essentially be to constrain our regular update rule of neural networks to ensure that the information from previously learned tasks is retained while finding parameters that will solve the new task in an efficient manner.
A solution that the Google DeepMind paper came up with to tackle problems related to scenario 1 is called elastic weight consolidation. Consider a situation where there are two tasks, task A and task B, and we want to train a network to perform well on both tasks. Let the gray ellipse represent the solution space where the network is good at performing task A, and similarly let the yellow ellipse represent the solution space where the network is good at performing task B. Now suppose we initially train a network on task A related training examples. We obtain theta A star, which represents a specific solution for task A. Now, when we start training the network on task B, the network can take multiple pathways to find a solution for task B. Our goal here is to restrict the movement of the solution along the red line so that it ends up in a place which is under the intersection of task A and task B related solutions. If we can enforce this, we can make sure that after training on task A and then subsequently on task B, the network performs well on both tasks.
Elastic weight consolidation essentially adds a cost term that emphasizes the weights that were important to the previous tasks. It does this to constrain the learning update rule to only move along the red arrow, which was described in the previous slide. It does this by utilizing the Fisher information matrix. The Fisher information matrix essentially describes the maximal variance of the posterior probability, that is, the probability that a weight was important given the previous training data set.
To test elastic weight consolidation, we did the following experiment. First, we defined the tasks that we will be using for training our network. Task 0 was defined as the classification of the original MNIST dataset. Task 1 and 2 were defined as the classification of MNIST where the input pixels of the images were permuted by a constant permutation. These permutations varied between task 1 and task 2. First, we trained the network on task 0 until a desirable network was obtained. Then, we stopped training on task 0 and introduced task 1 input examples, but we calculated accuracies for both task 0 and task 1. Subsequently, we trained the network only on task 2 examples, but calculated the accuracies for task 0, 1, and 2. This training process was repeated for two different kinds of networks, a LayNet 5 architecture and a simple MLP architecture with 3 hidden layers. Finally, the accuracies for multiple training results were measured and plotted. Just to clarify the idea of the permutation of the input pixels, we can see that in the case of task 0, we see the digit 5. In the case of task 1, the same image has been permuted by a specific permutation. In fact, all the images fed into the network during task 1 were permuted by the exact same permutation. Similarly, for task 2, a different permutation was used to permute the input pixels of MNIST.
These are the results that we observed when we ran our algorithm on the LayNet architecture. As you can clearly see, regular stochastic gradient descent suffers from heavy catastrophic forgetting. For task 0, which is the regular MNIST dataset, it is clearly visible that as soon as we change the training dataset to the permuted datasets, the performance at task 0 falls to chance probability, that is, at 10% due to the output dimension, which is 10. Whereas when you consider elastic weight consolidation, the accuracy does degrade substantially, but the accuracy still remains above 55%, which is quite good when we consider that we are oversaturating the parameters of this network. These are the results that we saw when we ran our algorithm on the multi-layer perceptron. As one can clearly see, stochastic gradient descent does not actually perform that badly in a multi-layer perceptron when compared to the LayNet 5 architecture. I think this is because of how a multi-layer perceptron absorbs the input vector. As each pixel has its own set of parameters that transform it from the input space into the hidden layer space, due to the nature of the permutations, going from one permutation to the other permutation, it is very possible that the set of parameters that are important for that pixel do not change much because that pixel may not be active high from one permutation to the other permutation. Thus, for stochastic gradient descent, because the parameters don't change that drastically because of the excessive parameterization in a multi-layer perceptron, the actual performance doesn't degrade that heavily either. We also implemented an algorithm to tackle scenario 2 catastrophic forgetting. Because our data wasn't ready by the time our presentation was recorded, that will only be discussed in the report. But scenario 2 essentially, how we tackled scenario 2 was we took MNIST and created 3 different subsets of MNIST. And we used the same experiment design as we did for the permuted MNIST as we did for the subset MNIST. Our future work could also involve different combinations of algorithms where we combined elastic weight consolidation along with incremental learning for learning more complex and more interesting tasks. Thank you.